All right, welcome to the fourth and final lecture of Unit 3, Forces Within. In this unit, we've been looking at the plate tectonic system, the solid Earth, forces within and on the surface of the solid Earth that have a great impact in shaping the Earth as humans interact with it, both over human timescales and also shaping the Earth and the surface morphology over long geologic timescales. Chapter 10, we're going to be talking about crustal deformation and mountain building. Two things that are also primarily driven by the tectonic system, which we covered in Chapter 7. In Chapters 8 and 9, we looked at earthquakes and volcanoes. Both are forces that have long-term impacts and work over long timescales, but also have very short catastrophic impacts that affect human systems. The crustal deformation and mountain building is fairly limited to long geologic timescales. Of course, mountain building is affected, or earthquakes and volcanoes interact or are part of the mountain building and crustal deformation system. But in this chapter, we're going to be looking at kind of the long-term geologic processes that shape the Earth. In general, deformation it's a general term, refers to changes in the original form or size of a rock body. Most crustal deformation occurs along plate margins. However, when the deformation occurs along plate margins over long periods of geologic time, those deformed areas can become part of more interior, more passive margin type environments where you wouldn't necessarily associate them with present day or current active plate margin activity. A great example of that is the Appalachian Mountains in the eastern United States, which at one point were along a very active margin, a spreading center or a divergent boundary, but now are in a relatively passive zone. So you oftentimes find deformed areas that are tectonically quiet, although the deformation you can usually assume occurred at a place and time where tectonism was much more active. Factors that influence the strength of a rock, that is its ability or likelihood of being deformed, are temperature. Higher temperatures will reduce the deformation threshold of rocks. That is, higher temperatures will cause rocks to be deformed much easier. Confining pressure oftentimes will affect it. Again, increasing pressure will increase the likelihood of deformation. Rock type. Some rocks are more likely to be subject to deformation. They have weaker planes of cleaving and fracture, jointing. Some minerals, same situation. And time. Deformation occurs, as you can imagine or intuit, quite slowly. That means that the longer a rock is exposed to either elevated temperature or compressive stress or confining pressure, they will be, actually I should retract that. The longer they're subject to higher temperatures and confining pressure, the more likely they will be deformed. This graphic down below shows some of the basic types of deformation. These are large scale. We're talking, in general, hundreds to thousands of meters or kilometers to hundreds of kilometers. You can have much smaller scale folding and faulting, but in general, anticlines and synclines are generally larger scale structures. Here we have what's called an anticline. That is an upwardly deformed or upwardly bent strata. It's a symmetrical fold, meaning the limbs on either side are plunging at about the same, or dipping at about the same angle. You have an axis of symmetry right down the middle. This syncline, or depressed kind of zone, concave structure, is also symmetrical. The limbs, the climbing limbs on either side are relatively at the same angle, and there's an axis of symmetry right down here. You can also have anticlines that are asymmetrical. That is, the axis of symmetry is not vertical, and synclines can be asymmetrical as well. So the symmetry can define or can give you information about the direction of stress, the geologic history. And then you can have what are called overturned folds, which are literally so asymmetrical that they've been overturned and looped back around on themselves. Most folds, which is a form of deformation, result from compressional forces versus, or in contrast to tension, pulling apart. So usually compression or convergence, which shorten and thicken crust. Anticlines are upfolded, as we saw in the previous slide, or arched. Synclines are downfolded. Anticlines are upfolded. Synclines are downfolded. And symmetrical or asymmetry, or symmetry, as in asymmetrical or symmetrical, or overturned, also characterize folding and on this scale. Plunging folds, plunging anticlines or plunging synclines, are actually where the kind of the fold or the ridge would disappear into the ground going up here, or would appear if it's a syncline going to the ground. We'll see that in a few slides. This is an example of a relatively large set of synclines and anticlines. Oftentimes they occur together because compressional stress kind of folds things in a ripple fashion. You can imagine if you were to take a bed sheet that was completely flat and push on one side of it toward the other side, you would get folds that go up and folds that go down. Those folds that go up are anticlines. The folds that go down are synclines. It makes sense if you think about a system like that. In this graphic, there's actually some faulting as well. So we have the anticline, or sorry, the syncline and the anticline, and then we have a fault here that truncates this section of the syncline, which would continue over here and move on up. Another example of anticlines and synclines, great places to see folding such as this. Anticlines and synclines on the scale of tens of meters to hundreds of meters are in road cuts, especially driving through the Appalachian Mountains of the eastern United States. Anytime these superhighways or state highways are cutting through large mountains where you see typically these lines striking down, which are really drilling holes for when they built the road, but you can oftentimes see really beautiful synclines and anticlines in road cuts like this. Sometimes during the summers you'll see groups of young adults stopped on the side of the road, usually with a couple vans, pretty plain vans, usually with state plates on those vans, and they're usually geology students who are on a field trip looking at road cut geology. It's a great way of getting access to layers that are below the surface of the earth. This is a fantastic example of an overturned set of anticline beds. Here you can see the beds going all the way over, and right here you see that curve, so you know it's part of one system. Same thing, overturned folds with the axis of symmetry, or the axis right down there, and the overturned limb on the bottom. And this is an example of a plunging anticline. So remember, the anticline is arching upwards. So this is the geologic sketch down below of what it would look like underground on this line, A to B. So if you sliced through the earth right along that line and went down, you'd see this is the A to B line, and that's kind of the vertical image of what this looks like right down below. But what this is a plunging anticline. That means that it kind of slides downward into the earth as you go further away. And how that impacts it, it's kind of a weird three-dimensional problem. If you can visualize things in 3 dimensions, you should be fine with this. It takes a little bit of concentration to imagine how a structure such as this under the ground, if it were tilted, that is not going completely flat horizontally across, would end up with seeing this type of folds on the surface that are kind of arching toward. And with a syncline, you would see the exact opposite type of structure. Domes are another type of folding and faulting, and they cause actual anticlines, and basins will ultimately cause synclines. But domes are usually caused by large intrusive plutons. That is, this is a pluton of granite. We remember talking about plutons in the last lecture. that are emplacements of magma, of solid crystallized rock deep in the earth, but that can cause superficial deformation. When you have a dome produced, oftentimes the layers will bend upward and you'll get an anticline. But as erosion takes place, you'll expose that central zone of the pluton. They can be circular or slightly elongated. They displace rocks upward, and the oldest material is usually in the core. You can see that from down here in the cross-section. The oldest material, which is the schist, which has been metamorphosed from the pluton intrusion. This is the oldest rock. If you didn't have the pluton here, these layers would be horizontal, and the oldest layer would have been on the bottom. The schist on the bottom, the pinkish layer next, and the yellow layer on the top. So youngest, this yellow layer here and here, is out here. The pinkish layer, which is the second youngest layer, is right in here. And then the central schist and granite is right here in the center. Basins, on the other hand, are areas that have had crustal deformation moving downward, either by loading on top. In this case, it's going to be glaciation, large expanse of ice sheets or a large thickness of ice during the last glacial maximum would have caused this area to subside, to sink down, to bend downward. And usually what you get there is you get emplacement of layers in the middle that are younger, and as you go outward, you get older layers that correlate to layers that were laid down in the basin as it was forming. Youngest rocks are in the core of a basin. These young rocks at the very top are in the middle. Now if we move outward along A or going toward B, start in the middle going toward B, you get to the older rocks successively till you get to the outside. Faults are fractures or breaks in rocks along which displacement or movement has occurred. Faults are another form of crustal deformation. They are deformation that happens in kind of more discrete or stepwise manner versus gradual kind of ductile deformation of rocks that we saw in the folding. Faulting can be described essentially three ways, and different types of faults are described by the direction of the blocks that are moving. So in a fault, there's something called the footwall, and there's something called the hanging wall. The footwall always has an exposure that is less than vertical. So the footwall, the angle of the footwall is probably, in this case, 60 degrees. Hanging wall is kind of the overhang block, which has a angle block of greater than or over vertical. In what's called normal faulting, which is tension pulling blocks apart, you can imagine which way the blocks would move. As you move this block this way and you move the hanging wall to the right, the movement of those blocks, the hanging wall moves down, the footwall moves up. That's a relative motion. So when the footwall moves up relative to the hanging wall, that's considered normal faulting, and that is always under tension. When you have compression, you can imagine that the footwall and the hanging wall would move in opposite directions relative to each other. We have that over here. It's called a reverse fault. When we have compressional stress, that is the blocks moving toward each other, the hanging wall will move up and the footwall will move down, and that acts to compensate or to absorb that movement, that compression, and allow those blocks of crust to compensate for each other. Now, an interesting type of reverse fault where the hanging wall moves up and the footwall moves down relative is something called a thrust fault, and that's where the angle of the fault is greater than greater than 60 degrees. I'm not sure exactly the exact number. I should know that. Anyway, this is where the hanging wall is kind of an extreme angle where the hanging wall moves back over and the footwall is moving down relative, but they're in a way almost moving horizontally underneath each other. It almost seems like a subduction type of thing. However, subduction is a really, really large-scale process on the order of hundreds to thousands of kilometers, whereas faults can be on the order of meters to hundreds of kilometers, much finer scale. And then the last kind of fault is called a strike-slip fault, and that's where there is no hanging wall or footwall. It's two blocks moving past each other, and these usually occur along transform boundaries that are tectonic margins that act to compensate for the kind of three-dimensional nature of plate movement. Strike-slip faults are oftentimes, in our culture, the most famous ones. The San Andreas fault is a strike-slip fault on a transform boundary, and that's where you get really, really rapid and dramatic movements of crustal blocks past each other, sliding past horizontally. Dip-slip faults are movement along the inclination or the dip of a fault plane. And dip-slip faults are what we just described in that last slide, reverse and normal faulting, where you have a hanging wall and a footwall. The hanging wall is the one that kind of overhangs or that's tilted over vertical, and the footwall is tilted to the subvertical. So the footwall is always the rock below the fault surface, and the other way of thinking of it is that the hanging wall is the rock above the fault surface. These are a type of fault that are generally categorized as dip-slip. And that's because dip is a geologic term for the angle at which rock kind of plunges in the direction into the earth. Okay, and slip is the idea of these walls or blocks of rock slipping past each other. So it's clear I've got my slides a little bit out of order. So these are just reviewing of the group of 4 slides that we saw before. We can review it quickly. In this dip-slip normal fault, we have the footwall moving up, the hanging wall moving down. It's due to tensional stress. Normal fault. Fault block mountains, which are common in the let's see, they're due to extension and tension. And so you often find those in rifting environments where crustal blocks are moving apart from each other. So the African Rift Valley, there's a rift structure in the Southwest United States, and you get these features, these large scale geomorphological features or superficial features called horsts and grabens. A graben is a dip-slip normal faulted block that is sliding down relative to other strata, and they're often between 2 ridges that are called the horsts. This is just a German term for this type of a tensional environment where you have crust moving apart, and in order to compensate, to fill in that area of these gaps that are being made, you have crust dropping down relative to other crust that stays in place. So horsts and grabens. Half grabens are where you don't have 2 horsts on either side, and you have these detachment faults that go along an arc of faulting down below. And again, this is all to compensate. These blocks of crust are basically filling in the space that is being created by crustal movement spreading apart or divergence. The reverse fault, which is another kind of dip-slip fault, is where the hanging wall moves up. Caused by strong compressional stresses. Dips are greater than 45 degrees. So here we have the 45-degree angle. You could have an angle steeper than 45, like 60 or 75 or 90. Sorry, not really 90, but 85, for example. Caused by strong compressional stresses moving inward. Whereas the thrust fault is a thrust with the dip is less than 45 degrees. Very similar to a reverse fault. And the strike-slip faults are not dip-slip. Displacement is horizontal and parallel to the trend or strike. So strike is the notion of where a layer of strata intersects the surface plane of the earth. So the strike in this case is this way. The dip in this case, there's really the 90-degree dip. It's the direction that or the angle at which the surface penetrates the earth. And they're caused by shear stress, that is, forces that are moving past each other in opposite directions. Faults can influence lots of surface processes, especially strike-slip faults. Drainage patterns can be dramatically affected with them, and erosion is oftentimes also strongly affected by the orientation, the strike, and the direction of movement of strike-slip faults, and to a degree dip-slip or reverse or normal faulting. Now, moving on past deformation, folding, and faulting, we get into orogenesis. Orogenesis is the process of mountain building. You can think of it in really, really simple terms. The processes that collectively produce a mountain belt is the technical definition, but just think of orogenesis or orogeny as mountain building. Okay, generally that happens due to deformation, folding, and faulting. This is a kind of a quick little schematic of an area that is just relatively level strata, and when you get zoom right in, when you get normal faulting, that is the hanging wall dropping and the footwall rising, you get what are called, well, these are an example of a mountain range that is built due to normal faulting. It's the Jackson Hole Range in Wyoming. It's part of the Rocky Mountain belt. Essentially, it's not necessarily caused by the same exact processes as some of the Rocky Mountain uplift, but it's what culturally we think of as all part of the same system, even though there's lots of different sub-causes for, or subsystems in those orogenic or mountain areas. Most mountain building occurs at convergent plate boundaries, and that makes a lot of sense. As you get compressive stress, the crust has got to move somewhere, and it's not going to move down, it's probably going to move up. This is a case of where you have a lot of compressive, what are called oceanic terrains. That is, oceanic material that's been accreted onto the continents. These are different terrains, and they all represent either different events of accretion, which is associated with a subduction, continental ocean or continental arc volcanism, and subduction and accreted terrains getting kind of adhered on due to the subduction process. This is an example of another convergent boundary where the Indian plate is essentially, we say slamming in it. We know how slow these things are moving, 9 centimeters a year, 10 centimeters a year. But in geologic time and space, that's pretty darn fast. India is colliding with the Asian plate, and the Himalaya mountains or Himalayan mountains are the uplift. So here we see the block schematic as India collides with Asia. We get a lot of faulting and fracturing and in fact some kind of rotation of crustal or tectonic blocks off. And you can see in graphical terms, it's a pretty interesting and complicated area in terms of where the compressional forces are, where the joints and fractures, the large-scale crustal fractures that are and faults that are occurring to compensate for that collision. This is another example of convergent boundary mountain building. As I mentioned earlier, the Appalachian Mountains, which is now a relatively passive area, it's an inactive continental margin. It's thousands of miles from the mid-Atlantic ridge where the active divergence is taking place. But at one point in time, if you look back and think of that slide that illustrated Pangaea, this area of the North American plate was slammed up against the European and African plate in a convergent kind of environment where continental collision was taking place, and then prior to that, oceanic continental subduction was taking place. Appalachian Mountains, which exhibit really dramatic folding, faulting, what's called valley and ridge provinces. You can see plenty of, if you think back to that plunging anticline photograph, you can see plenty of evidence of anticlinal and synclinal folding, sometimes plunging. And if you look at the larger scale topographic relief, you see how deformed really those Appalachians are. The coastal plain over here, which is really just outwash from those, from the erosion of the Appalachians, is flat and relatively devoid of large-scale geologic structure. But the point of this slide is to show you that not all areas that are presently folded and faulted or that are mountainous are, even though they may be in relatively tectonically inactive zones now, they all were formed, or for the most part were formed, by active tectonic processes at convergent boundaries at some point in the geologic past. This is an illustration that shows how lots of the major mountain ranges of the world are in areas of convergent boundaries. We've got the west coast of the North American continent up and through to Alaska. We have convergence here. We have convergence along the Andean mountain chain. Lots of Asian convergence activity. The island arc systems here are not yet continental arc systems where there's accreted terrains and mountain building, but they will be eventually. And the Himalayan uplift there is an area of massive mountain building, the most active mountain building presently, and it's due to the collision of the Indian and Asian plates. So Andean type mountain building, represented by the west coast of the South American plate, where oceans and continents are converging, and there's subduction of oceanic lithosphere beneath the continental crust. Subduction zone, the typical progression is a subduction zone forms, deformation begins down here and in the Pluton area. Continental volcanic arc forms, that is, you have active volcanism on the continental side due to partial melting of subducted plate material. And then eventually you get this accretionary wedge, which is this sediment from the ocean bottom that essentially gets scraped off and pushed up onto the shore, and becomes part of that continental shelf and continental crust. Sierra Nevada range and the California coast range are inactive Andean type orogenic belts. When you have two continents colliding, you get a slightly different progression. You still get usually get the oceanic subduction occurring before the continents actually collide, and you get the accretionary wedge. However, what eventually you get is this shallow sequence of marine sedimentary rocks from the colliding continent that will form very, very dramatic, somewhat, well, they can actually be quite large, sedimentary-based mountain systems. As we see this progression, as the continental crust moves toward the other block of continental crust, and eventually it will squeeze out the ocean, it will no longer be there, we have this massive area of marine sedimentary sequences that are uplifted and deformed and faulted. Ophiolite sequences are wedged in here, which are fragments of oceanic crust. They're very, very characteristic in terms of their mineralogy and lithology. And they're oftentimes pretty easy to recognize in field studies. So the Himalayas, the Pyrenees in Europe are both examples of continental collisions where you have marine rocks, marine sedimentary rocks, and placed at relatively high altitudes. In fact, some of the rocks high up in the Alps and the Pyrenees contain deep marine fossils, and in fact, Leonardo da Vinci was one of the first people credited with developing the study of paleontology when he observed or made observations of obviously marine fauna at high altitude in the Alps. He came up with what is essentially now incorrect assumption or incorrect hypothesis about how those rocks were emplaced. However, he did make those observations of what are deep ocean fossils at very high altitude in continental Europe. Continental accretion is the third mechanism of mountain building, and that's where small fragments of crust collide and accrete. Accrete means to kind of adhere onto or glue onto. So it's where small fragments of crust collide and accrete to continental margins. These accreted crustal blocks are called terrains, or oftentimes shortened to accreted terrains, and geologists know what they're talking about. They oftentimes occur along margins that are similar to the Pacific coast. Somewhat quiet right now with small blocks. There's some interesting small plates that exist on the eastern side of the Pacific plate. The Farallon plate is an ancient one. The Juan de Fuca plate. These small plates can cause really kind of complex but small scale tectonic features. Accreted terrains are one of them. So here we have a formation of a sedimentary platform. These sediments are accumulating from outwashing off of the continent, and they accumulate where the shelf protrudes out onto the rise. But as you get subduction, those shelf sediments get deformed and faulted, and eventually pushed up high enough so that you get a coast range. Basically, it's an uplifted accretionary wedge where you don't get this typical andesitic volcanism like you otherwise would in the Andes type mountain building, but you still get in place plutons that come up, and there is kind of magma migration upward through the crust. It's just not as dramatic as the Andes type. This is another example of how that happens, how it happened in the to generate the Appalachian Mountains. 600 million years ago, you had North America moving toward Africa. Lots of a microcontinent and island arcs due to this complex series of subducting oceanic slabs and oceanic continental slabs, where you were getting kind of extrusive orogenic episodes. 150 million years later, this microcontinent has been swallowed up by the North American plate moving forward, and you have what's called the Blue Ridge or the Western Piedmont. The Blue Ridge is exactly what it says. It's the Blue Ridge Mountains, or the Alleghenies, the Catskills, the Green Mountains, White Mountains of New Hampshire, on down into the Smokies of North Carolina, and into Georgia. As time progressed, the island arc again was swallowed up again by the North American and Blue Ridge Piedmont, and so then you get what's called the Carolina Slate Belt in this case. But it's a zone of highly metamorphosed silt and mudstones that were deposited in very quiet or shallow marine environments, and eventually Africa and North America collide completely. And you have the centralized orogenic mountain belts that's built from the faulting and folding and deformation of that collision. But you also get what's called the Valley and Ridge Province to the west and to the east, which are kind of rippled, deformed mountain chains where you have repeated valleys and ridges, and are quite typical of continental collision. And that spanned an area of about 600 to 300 million years ago. Soon after, you started a period of divergence. So about 300 million years ago, 250 million years ago, rifting started to occur in that zone, and rifted to the point where now we have our Atlantic Ocean that separates Africa from North America. The Valley and Ridge and the Appalachians ended up with the North American plate. Now, as we move on to the end of chapter 10, we need to talk about why continental crust is so much thicker, and why it tends to move up when collisions occur. And that has to do with buoyancy, or in geologic terms, the principle of isostasy. Now, evidence for crustal uplift typically includes wave-cut platforms that are high above sea level. That is, as crust moves up through an ocean environment, when it reaches the sea surface, where there's a lot of wind and wave action, and remember, crust is uplifting in generally terms very, very slowly, inches per year kind of thing. When it reaches the sea surface, where there's wave action, it creates shorelines, and shorelines are high energy, very high erosion environments. So what you'll often get is, as crust is uplifting, or blocks of earth are uplifting, as they protrude through that sea level surface, the wave action will erode those things and generate very, very flat and obviously eroded areas, or wave cut areas. As those blocks continue to rise up, those areas of wave cut erosion will become stable again and no longer be eroded, but the evidence for that erosion remains, and as crust blocks are uplifted, geologists can often find wave-cut platforms, which is fairly compelling evidence to support the notion that crust has uplifted in that particular area. But the reason for uplift, not so easy to determine. So isostasy is the concept of a crust which is less dense than upper mantle, and oceanic crust is floating in gravitational balance, or has buoyancy relative to the material below it. When weight is removed from any crust, it kind of balances and has to rise up. You can think of it as a boat floating through the sea. If you have a lot of weight in that boat, it's going to ride lower in the water. When you start to remove mass from that boat will rise up and will draw less. Same thing with continents. You can envision continents, even though Alfred Wegener turned out to be wrong about continents drifting through a sea of magma slicing through oceanic crust, in some facets that analogy is fairly accurate, and that is that continents essentially float in the upper mantle. When mass is removed from the upper or the higher zones of continents or higher altitude areas of continents, isostatic adjustment takes place, and those continents can rise up, and you get actually uplift or movement upwards of continental blocks. This is an example of how that process would work. In the top slide, you have a large mountain range that's relatively high. You can see its relatively jagged peaks, which essentially implies that it hasn't been eroded very much. It's either caused by volcanism or continental accretion and orogeny. As over time, as that material from the top undergoes the natural process of erosion, material from up high, streams and wind and snow will erode that material. Some of it will end up in the ocean. It deposits in the shelf. Others will deposit down off on the continental crust inland. But essentially this higher mountain range is lowered down, and you can see how these plutons down below start to be exposed, these batholiths, as the mountain range is eroded. Some of that sedimentary material, some of that eroded material is transported off the coast and now is deposited in the continental shelf and slope, and other is deposited off on the flanks of the mountain range there. Further on in time, this area is almost completely flat. But what you'll notice happened underneath is that when you started off with your big mountain range, the root of the mountain or the base of the mountain was also of similar kind of size and scale. As you remove material down here, uplift causes material to kind of bounce or bound upward and buoyant due to buoyancy issues or isostatic adjustment. The bottom of the crust kind of moves up, and so even though you're eroding downward, the crust is moving upward. So the rate of erosion actually exceeds the rate that the altitude is reduced, if that makes sense. And eventually, when you truncate the whole entire mountain range, the thickness of the crust is compensated from down below, and has also had bounces kind of or isostatically adjusts upward. In deep time or geologic time, convergence and compression is usually the first step. When you have convergence, compression, or compressive forces, you generate uplift or orogenesis. You generate mountain building. And then erosion and gravity take over and cause these mountain ranges to naturally kind of subside in terms of altitude. So it's kind of a natural, or it's a geologic cycle per se. Natural forces of convergence and compression, followed by mountain building or increasing altitude at the surface, followed by erosion and gravity, which then take over and reduce the mass of material on the surface. And eventually once you get gravitational collapse, you get stretching and thinning, which is a positive feedback and causes even more reduction in amplitude or altitude. So compressional forces dominate first, gravitational forces dominate second. So that's it. This is a relatively short lecture, but it kind of sums up all the forces that work from interior or the inside of the Earth that manifest themselves on the surface in terms of the geologic structure of the surface, as well as the processes that affect humans and all organisms, or the biosphere on the surface. So hopefully that summed it up pretty well for you. The next section is going to be, yes, I am looking at my book. The next section, Unit 4, is Deciphering the Earth's History. That's the really good stuff. We're going to talk about geologic time and the Earth, the evolution of the Earth's surface and interior throughout that time. So stay tuned for Unit 4, and remember to review your textbook material for chapters 7, 8, 9, and 10, and take the quiz when you're ready.